Hi, welcome back to My Smart Learning. It's me, Mr. Mien, with you for your science and physics lessons. Today we're looking at internal energy and specific latent heat. Again, I'm getting two lessons from your physics textbook, your computer textbook. I'm merging them into one, so I should be able to fit it in one go. Learning objective: what is internal energy and what is specific latent heat? Okay, recall quiz, virtual high five if you want one. Number one, what does the particle diagram look like for a solid, liquid and a gas? Number two, what's the temperature for when water freezes? Number three, what's the temperature when water melts? What's the temperature for when water boils? And what's the temperature when water condenses? Pause the video, have a go at answering those questions, and once you're done, you can unpause it now and we'll go through the answers. Right, number one, solids, remember, regular rows and regular columns even, regular columns and regular rows. So circle, 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 looks like a square shape, and they're all touching, there's no gaps between them. Liquid, irregular, all over the place, but the particles are touching with some little gaps between them. Gas, all far apart, okay, and only a few particles. Water freezes, 0 degrees Celsius. Water melts, again, 0 degrees Celsius. We have a trick question there. Number four, water boils at 100 degrees Celsius. And water condenses at also 100 degrees Celsius. Again, trick questions. Those two are the same. Those two are the same. Right, internal energy. This is quite a complicated idea to get your head around. In any substance, there's going to be particles in there. Those particles are going to be moving about, and they can't just move around by themselves. There has to be energy in them for them to move, and that's what internal energy is. Internal energy is the sum, the total amount of energy that those particles have, the amount of energy inside of them that's causing them to move about. And it's a sum, which basically means adding up two numbers, or adding up numbers. It's a sum of two parts. Those two parts are this. It's all of the kinetic energy of the particles plus all of the potential energy of those particles. So here's the proper definition. The energy stored by the particles of a substance is called its internal energy. This is the energy of the particles that is caused by their individual motion and positions, because some of them are going to be in that position, they're going to be moving about from here to here. The internal energy of the particles is the sum of the kinetic energy they have due to their individual motions relative to each other, which basically means they're moving about compared to each other, and the potential energy they have due to their individual positions relative to each other. So the potential energy, so this one's up here, that one's down there, this one's got more potential energy than that one. Now here, we're not talking about the kinetic energy of the thing moving. So we're not talking about here is my projector remote and it's moving from here to here. It's not talking about that kind of kinetic energy. And it's not talking about potential energy in the sense that here's my remote, it's on the table, I'm going to lift it up, it's gaining GPE, it's gaining gravitational potential energy. It's not talking about that either. It's neither of those types of KE and GPE. It's talking about the particles inside the matter. That's why it's a bit of a tricky notion to get your head around. The particles are moving. In a solid, they're vibrating, so they've got kinetic energy. They've also, relative to each other, have a position, so they've got a store of energy if they're higher up than the other one, and so on. So it's the total of those things added together is the internal energy of a substance. So that's what it is, and that's why, I mean, that's a whole lesson in itself, and that's why I put these two lessons together, because that's quite a quick thing to get through, but it's a complicated thing to comprehend. Now the next thing, the bit of calculations now. This equation you don't need to memorize, but it's useful if you do, because it's not a hard one to memorize, because it's better to memorize all your formulae, and then you can just straight away do the question. If some of the formulae are given to you in the exams, most of them are not, so most of them you have to memorize. One or two of them they give you, and this is one of the ones that they usually give you. The thing is, it's a quick one to memorize anyway, and if you need it, you can always go back and check it to see if you're right. But by memorizing formulae for your physics exams really helps you to understand the physics, because physics can be very complicated to get your head around and comprehend. So try to memorize your formulae. It's really, really, really important that you memorize them, and rote fashion, parrot fashion, and just keep going over them over and over again frequently. The more repetition, 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 that's the thing that's to help you memorize stuff. So the specific latent heat of a substance is the amount of energy needed to change 1 kilogram of that substance from one state to another state without changing its temperature. So what does that mean? Well, if you think about the last lesson, I'm going to go over some of the stuff I did last lesson. When that graph goes up and goes flat, remember, if I'm turning ice into water, when it goes from ice, it goes flat when it's a mixture of ice and water, then it goes up again when it's turning into a liquid, that temperature stays flat, and that's the point at which it's changing state. Now, the energy needed to change 1 kilogram of that substance, so 1 kg, let's say, of water is 1 litre of water, so that's like the same size as your Robinson's fruit squash bottles. Okay, there are other squash companies available, but that's the one that came to mind. But 1 kg of water, so how much energy do I need to put into that 1 kg of water to change all of that ice, let's say it's a bottle of ice, into water? That's what it means by specific latent heat. Okay, so the equation is simple. E equals ml. So to memorize it, E equals ml. E is the energy in joules. M is the mass in kilograms. It has to be measured in kilograms. And the L represents the specific latent heat. And the units for that is joules per kilogram, because it's a formula triangle again. E equals ml. So E's at the top, M and L are at the bottom. So if I want to calculate the mass, I'd cover up the mass, it would be E over L, so energy divided by the latent heat. If I want to work out the L, which is what this will get you to do, it's going to be E over M. Energy divided by mass. So there you go, energy divided by mass, joules per kilogram. So mass needs to be in kilograms, you need to convert it into kilograms, specific latent heat is in that unit, and then energy is going to be in joules. Okay, so, shall we have got some examples before we do that? Just quick definition though, there's 2 types of specific latent heat, because look, I've got specific latent heat of fusion, and I've got specific latent heat, you'll see on the next page, of vaporization. Now I'll come back to these guys in a second. When he's talking about this one, you draw the L and you do a subscript, which means lower down with the F. F stands for fusion. What are we talking about here? Fusion means to join. When you fuse something, you join it together. So when a liquid, when water turns into ice, it's fusing, it's joining together. The bonds are being formed between the liquid particles. Now, there's 2 different latent heats then. There's one where you turn water into ice and ice into water, and then there's the other side on the top of the graph where you've got liquid into gas or gas into liquid. So that's called vaporization. So the bit at which you turn a solid into a liquid, so the melting point, so the specific latent heat of fusion of a substance is the energy needed to change 1 kilogram of that substance from a solid to a liquid. So it's melting point without changing its temperature. So the temperature stays flat, stays the same. And then we talked about the units, joules per kilogram. The energy transferred to a solid at its melting point and mass m of the substance is shown by this equation. So again, like we said, E equals ml. The F just stands for the fusion bit, so it's E equals ml. And then if you rearrange that, L equals E over m, because you've got energy divided by mass. So energy divided by mass. Simples. The last one is vaporization. The specific latent heat of vaporization, we use a little V to represent the vaporization, LV, of a substance of the energy needed to change the state of 1 kilogram of that substance from a liquid to vapor, or it's basically its boiling point without changing its temperature. And again, the units are going to be joules per kilogram, and it's exactly the same formula. E equals ml with a little v, or if you rearrange it, the L with a little v is E over m. Simple, same thing. So let's have got some calculations then. E equals ml. Number 1, how much energy is needed to melt 2 kilograms of ice if the latent heat of fusion is 334 kilojoules per kilogram? So it's given to me as kilojoules per kilogram. So I'm going to return, that's going to be end up in, it's going to give me an answer in, it's giving it to me in kilojoules, so you're going to turn that into thousands, so it's going to be thousands, okay? So, because remember, it's got kilojoules per kilogram, so the answer is going to be in kilojoules, okay? Because it's giving me the fusion in kilojoules, so the answer is going to be in kilojoules. So, because it's the energy I want, how much energy? So there's the energy in joules or kilojoules, depending on what I get given here. and then because this would have been 334,000 joules per kilogram. So instead of writing 334,000 joules per kilogram, you just write 334 kilojoules. So ml, so m is what? 2, so put 2 there. The L is that, 334, put that there. So 2 times 334 equals 668 kilojoules, or 668,000 joules. Question 2. What is the latent heat of vaporization if it takes 1,132.5 kilojoules of energy to evaporate 500 grams of water? So, what am I going to do here? It's asking me what is the latent heat of vaporization. It's asking me for L. I need to work out what L is. So I need to, it's giving me the joules, so I've got the energy, so I've got 1132.5, and I've got the mass, which is 500, and I want L. So if I want L, I'm going to do the energy divided by the mass, so E over M. So E is that, divided by that, should give me the answer. No, it won't. Why won't it? Because I haven't converted the mass. The mass has to be in kilograms. So that needs to be 0.5. So 500 needs to be turned into 0.5 kilograms. Now I can use this number, because as long as I just make sure that I put this as kilojoules per kilogram rather than joules per kilogram. So the latent heat is energy divided by mass. There's the energy. There's the mass. I've changed it to 0.5. So there you go, it's 2,265 kilojoules per kilogram. Okay, so obviously if I converted that back into joules, that will be 2,265,000 joules per kilogram. Okay, it shows you that you need a lot of energy to vaporize just half a litre of water. That's a lot of energy. Okay. So those are a couple of typical kind of questions you can get. Just remember, if a simple one is like that, E times equals ml, you just multiply them together. If it's L you want, you have to rearrange it, so it's E divided by M. Just make sure you use the correct units. If it's grams, you need to turn it to kilograms. If it's giving you the question in kilojoules, you can give the answer in kilojoules, but just make sure that you give the answer to the correct units. So here, because the numbers are big, we're using kilojoules rather than joules. Okay, because it could be kilojoules per kilogram, which is just thousands of joules per kilogram, as long as you got the right units. So, to finish off then, just remember, liquid to gas, you heat it, it evaporates or boils. Condensation is when it goes from gas to liquid. Freezing is when it goes from liquid to solid. And melting when it goes from solid to liquid. We did this last time, so it's just a reminder of last time. But the reason why I'm showing you this again is because you got to remember this specific latent heat of vaporization and of fusion is all to do with this graph. You heat it up, the temperature starts to rise. The particles are gaining potential energy. Okay, sorry, here as the temperature starts to rise, the temperature is rising. If the temperature is rising, the particles gain kinetic energy. My bad, got it all the way around there. Kinetic energy. So the temperature is rising, they're getting more kinetic energy because the particles are moving around more. But here it's a solid, they're vibrating more because they're a fixed point. Okay, and the higher the temperature, the more they vibrate faster. So they're gaining kinetic energy. Then it goes flat. This is the point where the temperature doesn't rise anymore. So they're not gaining any more kinetic energy. What they're gaining is potential energy. So here, the potential energy is gaining. So all in all, the internal energy is increasing, but the up bits are the Ke bits that are increasing. The flat bits are the potential energy stores increasing, and that's going into breaking those bonds that are holding those particles together, and then they break, and until all of them are broken, that's when the temperature starts to rise again. So at the melting point, we've got Ke increasing, then Ke stops increasing, potential energy starts to increase, and then again, once every single bond between the ice particles, the solid particles break, then the temperature starts to rise again. And that's where the Ke starts to rise again. So Ke starts to rise again, and then it starts to boil. So we've got liquid and gas. So now no longer KE stays still. It's the PE now. The potential energy starts to increase until every single liquid particle breaks away and turns into a gas, evaporates away, boils away. So the PE, the potential energy, starts to rise there. And then once you've gone beyond that boiling point and you turn it to super steam, like a superheated steam, that's where the kinetic energy starts to rise again. So when the temperature is rising, the part of the internal energy that's rising is the kinetic energy. When the temperature stays flat, when there's a changing of state, it's the potential energy that starts to increase. And here is where the bonds between the particles are starting to break. Okay, and we showed it with this graph as well. So we can see this bit here is called the latent heat of fusion. This bit here, the green one, is showing us the latent heat of vaporization. Either way, E equals mL, or L equals E over M. So, to finish off then, key points: increasing the temperature of a substance increases its internal energy. We know that because its Ke increases. The strength of the forces of attraction between the particles of a substance explains why it is a solid or a liquid or a gas. When a substance is heated, if its temperature rises, then the kinetic energy of the particles increases. If it melts or boils, the potential energy of the particles is increased. The pressure of a gas on a surface is caused by the particles of that gas repeatedly hitting the surface. But that's what we're going to focus on next time. When you see my lesson, it's going to be on gas pressure. Last thing then, latent heat is the energy needed for a substance to change its state without changing its temperature, 1 kilogram of that substance. Specific latent heat of fusion or of vaporization is the energy needed to melt or to boil 1 kilogram of a substance without changing its temperature. In latent heat calculations, use the equation E equals mL. The specific latent heat of ice or of water can be measured using a low voltage heater to melt the ice or to boil the water. Okay, so that's the little practical that you can do to work that out. Here's some exam questions for you to have a go at. You've got the information, some more challenging, harder exam questions for you to have a go at. The PowerPoint will be sent to you on Show My Homework. Hopefully you guys have learned something today, and I hope to see you next time when we do gas pressure. Hope you've learned something on My Smart Learning with Mr. Meehan today in your physics lessons, and I'll see you next time on gas pressure. But before I forget, something you can't buy in the shops, especially because they're not going to be open for another 2 weeks because the lockdown is still carrying on. Some non-essential shops are starting to open, but you can't buy one of these in the shops. Virtual high five from me.